This video is part 3 of a presentation lecture on section 7.5, Math 311, a course in linear algebra at Western Illinois University. So this is video number 3, but this is actually, we're looking at part 2 of the notes I just posted. So we're going to continue this discussion of singular value decomposition, and we're going to, in particular, talk about pseudo-inverses of matrices. Okay. So what we're going, so pseudo-inverses, we know that, you know, when you have square matrices, they may or may not be invertible. Okay. But we're going to see, and we're going to see that if we just take arbitrary matrices, like, you know, any n by n matrix, we're going to see that they do have something similar to an inverse. However, it's going to be a little bit different than the traditional, the regular inverses that we've been talking about all course. So let's just review singular value decomposition. So again, throughout this talk, A is going to be an n by n matrix, and we showed that the product A transpose A, not only are the eigenvalues real, but they'll be non-negative. So we take the square roots of the positive eigenvalues, and those are the singular values of A. All right. So sigma 1 or sigma r are the singular values of A, because their squares are going to be the positive eigenvalues of A transpose A. And we showed last time that the R, the number of non-zero singular values, is equal to the rank of A. Now the singular value decomposition of A, remember, means we can write A as a product of these three matrices, U, sigma, and V transpose, where U is an n by m orthogonal matrix, V is an n by n orthogonal matrix, and sigma is this almost diagonal matrix, where the first R elements on the diagonal are going to be the singular values, and you have zeros everywhere else. However, this is not a square matrix. This is an n by n matrix. Okay, so that's why we have these other zeros here. All right. So we said this was the and we got the V from the eigenvectors of this matrix, and then we did the calculation from them. We calculated the columns of U, and that gave us everything we needed. All right, now we want let's look at this matrix, big sigma here, a little closer here, and just note that because this is n by n, the transpose will be n by m. Okay, so when we take the transpose of sigma times sigma, we get a square matrix, which is n by n. Okay, and as you would suggest, these entries are just going to be the squares of the singular values. And so we get something similar if we switch the order. If we take sigma times sigma transpose, this is m by n, this is n by m. So then this time we get an n by n matrix, and once again we get the squares of the singular values on the diagonal. All right, now we're going to define another matrix based on these singular values. We're going to define it sigma plus, and this is an n by m matrix, and it consists the only non-zero values are going to be the reciprocals of the singular values, and we're going to start down there the diagonal here. Only this is not necessarily a diagonal matrix. Okay, so this is sigma plus, and I hope you don't get confused this too much with sigma transpose. Okay, so I try to make the plus sign as distinct as I can here. So a couple of observations about this. As we said, this is an n by n matrix, and in fact, what we have is if we multiply sigma times sigma plus in either direction, we get these following matrices. Where if we take sigma by sigma plus, again, this is an n by n matrix, this is an n by m matrix, So we get an m by n matrix where we have the we have the the identity matrix of size r in the upper left-hand corner here. So we basically we have r1s starting from the top left corner, and then zeros everywhere else. Okay, and this is because we're just, these are reciprocals. We're multiplying them out. Okay. Similarly, if we switch the order again, we get again something like similar. It's just that we get an n by n matrix this time because this is n by m and this is m by n. Okay, and again the ones will be on the diagonal here. So that's something to keep in mind. Of course, if it's the case where r is equal to n, then this whole thing is just none of these. So this is I like if r equals n, then this whole thing, this matrix here is just going to be the identity matrix. Okay. Now, so with that in mind, we're going to use this sigma plus to define the pseudo-inverse of A. So, what is the pseudo-inverse of A? Okay, well, call it A plus, and it's just if V and U are the same as it was before, this is just V times sigma plus times U transpose. And this does work out okay. This is an n by m matrix because V, remember, is n by n. Sigma plus is n by m, and U is m by m. So the dimensions work out okay. If we observe a couple things here, if we multiply A transpose, A times A plus, what we get is after substituting, we see that, remember that V transpose and V are inverses of each other because V is orthogonal, so this goes away. And then we already know what sigma times sigma plus is. It's this matrix, right? So we get U times this matrix times U transpose. And if we multiply them in the other direction, H plus times A, we get V sigma plus U transpose U sigma V transpose. U is orthogonal, so these cancel out. They're inverses of each other. So this becomes sigma plus times sigma, and we all know that that's going to be this matrix here. Okay, so we get V times V transpose. Now, one thing that you should keep in mind that in the case where M and N are equal and A is invertible, that in other words, A is just a regular invertible matrix, M and N are equal to each other because we're talking about a square matrix, and R is also equal to N and M because if it's invertible, the only way a square matrix can be invertible is if its rank is equal to the number of rows or the number of columns, right? So, in that case, this matrix and this matrix just become the identity matrix of size n or m, and then we get here the U's cancel, U and U transpose cancel out. Here the V and the V transpose cancel out, and we get the identity matrix. Okay, so in other words, in this case, the pseudo-inverse is the actual inverse of A if A is already invertible from the start. Okay, now remember when we did this in the first part of the lecture, we were trying to find, solve an equation, AX equals B, where A was not necessarily a square matrix. And we said that we could solve this. We could get this might not have an exact solution, but it could have a least square solution. That is, we could find an x so that the distance between this vector and this vector is as small as possible. And we could do that as long as the columns of A were linearly independent, because in that case, we were using the fact that if the columns of A were linearly independent, that meant the rank of A was equal to n but that also meant the rank of A transpose times A was equal to N, and therefore A transpose A, or A transpose A was itself invertible. And in fact, we used that inverse to help solve this equation. We're going to see that this actually how this is connected to the the pseudo inverse. So if we look at, so basically, remember what we did was for the least, finding the least squares, we were taking we were taking the inverse of A transpose A and multiplying by A transpose, and then multiply it by B, and then that turned out to be X. Okay. So, well, what is this? If we use the singular value decomposition of A, so we can replace A transpose. So here we replace A with U sigma V transpose, and we get this. And then we simplify it. So in this first step, what we do is we're taking the transpose of the product of these three matrices. So this by the properties of the transpose, this would be V transpose transpose. That's V times sigma transpose times U transpose. Okay, and then we still have U sigma V transpose. And notice the U transpose and U are still inverses of each other, so this is just IM. So this cancels. So we just get V sigma transpose sigma V transpose. Okay, take the inverse of that. And then in this next step, we also use the properties of the transpose. The transpose of this product, again, is V sigma transpose U transpose. Okay, now we know what sigma plus, and again, this is, yeah, we're not bringing sigma plus in yet. This is transpose. But we're using the fact that we know that sigma transpose is right here. So we can replace sigma transpose sigma with this square matrix in this. And in this case, we have R is equal to N. So these elements just go all the way down the diagonal. Okay. So we get this. All right. Now, by the properties of inverses, the inverse of this product would be the inverse of this times the inverse of this times the inverse of this. So the inverse of V transpose is the inverse of V, which is just V. The inverse of this matrix, this is easy, it's diagonal, so we just take the reciprocals of the diagonal elements. And then the inverse of V is V transpose. So that's how we get this here. And then we still have the V sigma transpose U. This time the V and V transpose cancel each other. And so we get, this goes away, and we know that sigma transpose is this. And then if we, just to be a little careful, this is an n by n matrix, and this sigma transpose is an n by m matrix. Okay, so this does work out. And we can see that these we're going to get some cancellation. Well, we'll get some cancellation, but not complete cancellation. For example, so sigma 1 times sigma 1 divided by sigma 1 squared is going to be 1 over sigma 1, and so on. So we get the reciprocals of all the singular values here, and we have 0, 0. Remember, this matrix will be n by m, and in fact, this matrix right here is precisely sigma plus, the way we define it, right? So we get V sigma plus U transpose, which is just A plus. Okay, the pseudo inverse of A. So it turns out that when we were calculating this to do the least squares thing, we just did we were actually computing a pseudo inverse without even knowing it. Okay. Now we're going to see that we can actually do this. We're going to see what we can actually. This still will make sense if the rank of A is not n. That even if the columns of A are not linearly independent, we can still talk about a pseudo inverse, and we can still use that to find the least square solution to this. All right. So before that, let's just do an example. Some of these examples are a little stupid. The first one definitely is a little stupid. So let me just make sure we're all set here. Okay, so here we're just letting A be a 1 by 2 matrix, right? So M is 2, N is 1, or try again. And number of row, we have 1 row, 2 columns, so this is a 1 by 2 matrix. Okay. So A transpose A, and what we're going to do is we're going to try to find the pseudo-inverse of this. So this is A transpose A is going to be 1, 3, 1, 3, and this will be the 2 by 2 matrix 1, 3, 3, 9. Okay. All right. So that now what we want to do is we to find the singular value decomposition, we write the get the eigenvalues first. So take the characteristic polynomial. So we take the determinants of 1 minus lambda, 3, 3, 9 minus lambda. Okay, and this is going to be 1 minus lambda, 9 minus lambda, minus 9. And if you multiply this out, you get lambda squared minus 10 lambda. And this, you factor out lambda if you want. And it's pretty clear that the eigenvalues will be 10 and 0. Okay, so we can let lambda 1 equal 10. We'll take the biggest one first, and then lambda, you always split the zeros be the last. And then this means that sigma 1 is the square root of 10, and sigma 2 is still 0. Okay. Then, let's find the eigenvectors when lambda 1 equals 10. If we plug 10 in here, 1 minus 10 is negative 9, so we get negative 9, 3, 3, and 9 minus 10 is negative 1. Okay. We like to find the null space of this matrix. I'll spare you some of the details, but I think it's pretty clear. We can see that these rows are multiples of each other, and it's pretty clear, hopefully, that the solution will be 1, 3. Okay, this column vector 1, 3 will be an eigenvector. Okay, so this is 0. So this is our eigenvector, and so we want to normalize this. V1 then is just the normalization of this. The length of this vector, we take 1 squared plus 3 squared, that's 10. Take square root of 10, that's the length. So we take 1 over square root of 10, 3 over square root of 10. That will be our V1. If we take lambda equals 0, and here we get 1, 3, 3, 9. And again, it's not hard to see that 3, negative 1 will be in the null space of this matrix. So 3, negative 1 will be our eigenvector. And once again, this length will be the square root of 10. So when we normalize it, we get V2, and that will be 3 over square root of 10 and negative 1 over square root of 10. Okay. So our matrix V is going to be 1 over square root of 10, 3 over square root of 10, 3 over square root of 10, and negative 1 over square root of 10. Okay. Now, to find U, U1 is going to be 1 over sigma 1 times AV1. This is going to be 1 over square root of 10 times 1, 3 times 1 over square root of 10, 3 over square root of 10. And if you multiply this out, you get 1, but this will be 9 over square root of 10, or 1, it'll be 1 plus 9 over square root of 10, so it'll be 10 over square root of 10, divided by the square root of 10, well, that just becomes 10 over 10, and believe it, when the smoke clears, we get 1, and actually this is a 1 by 1 matrix. Okay, and we can stop here. We don't have to find, remember, M in this case is 1, so we can stop there. This is the only thing we need. So so in fact U in this case is just going to be a 1 by 1 matrix where the only entry is 1. All right. So then, so that's U. This is V, and of course sigma is going to be consists of this is square root of 10. Okay, and I should remember that this is well, actually, in this case, well, sigma is going. Well, I can tell you that sigma is going to be square root of 10, 1. But what we really want is sigma plus, and that is going to be 1 over square root 10 and 0. By the way, this should be a 0 here. Okay. All right. So the pseudo-inverse A plus is going to be what we said, V sigma plus U transpose. So this is going to be V times sigma plus, okay, times 1. Okay. Again, this is 2 by 2, this is 2 by 1, this is 1 by 1. Okay, so our final answer is going to be 2 by 1. And if you multiply this out, this actually turns out to be, this 1 doesn't really contribute anything. This is 1/10 plus 0. So this first entry will be 1/10, and then we have 3 over 10 plus 0, so that's 3 over 10. So 1/10, 3/10 is our pseudo-inverse. Okay. All right. So that is one example. It's kind of almost a silly example, but we'll do a more interesting example in the next video.